In this video, we'll be discussing coefficient of determination, r squared. Hopefully you've seen the video where the gentleman described how you interpret r squared in context. We'll get a little more specific and give you a few things to add to your notes for how r squared is actually determined. First, a preliminary definition, variance. Variance is the square of standard deviation. And much as standard deviation is a measure of spread, variance is a measure of spread. Thus far, we have discussed exclusively standard deviation in lieu of variance because standard deviation is in the same units as the mean. If the mean is miles, standard deviation is miles. If the mean is ounces, standard deviation is ounces. Variance is in the square of those units, so it's a little harder to understand what variance is representing unit-wise. But as we advance in statistics, we'll see that variance behaves a little bit better mathematically, and we're able to oftentimes use it where we can't use standard deviation. The symbols that represent variance are just like standard deviation, only squared. The population variance is sigma squared. Just like the population standard deviation is sigma, population variance is sigma squared. The sample variance is s squared. So you can see that these symbols are the same symbols as their standard deviation brothers. Okay. Coefficient of determination. R squared, and sometimes you'll see this capitalized, sometimes it's lowercase, doesn't really matter. Coefficient of determination is the fraction of variation. The fraction of variation, and by variation we mean change in. When you see fraction, you can think percent. The fraction of variation in y explained by the variation in x. Alright, we're now going to refer back to a problem we've done previously. The fat and calorie contents in some hamburgers. So here was our data. Fat and calories. 19 paired with 410. 31 with 580. 34 with 590. 35 with 570. 39 with 640. 39 with 680. And 43 with 660. This data is on page 206. This is number 57. Enter this data in list 1 and list 2 at this time. Once you have your data in there, we're going to graph the data, making sure your plot 1 has been selected and you've selected the scatter plot. We will zoom 9, and here's our scatter plot. You can see it is indeed a positive association. As the number of fat grams increase, the number of calories tend to increase. And it's definitely linear, and it looks fairly strong. Alright, so we'll perform our regression now. Stat, calc, number 8. We want our X list to be at list 1. We want our Y list to be list 2. And we want it to store our regression equation. Vars, Y vars, function number 1, and then Y1. Okay, then we go calculate. If you have not turned on your diagnostic, you need to, so we can see R and R squared here. Well, I want to look at those two values. R is approximately 9.6. R is approximately 0.9606, and R squared is approximately 0.9228. Alright, and we can think of this R squared as a percent, so this is approximately 92%, 92.3%. Alright, so we can say that 92.3% of the change in calories is explained by the change in fat content. Well, what does that mean? How do they arrive at that? First, it is literally the square of this value R. If I take 0.9606 and square it, we'll get approximately 0.9280. Let me show that. 0.9606 quantity squared is going to be remarkably close to 0.9228. There you see it. So one way to find R squared is to simply square R. Okay, but now I want to see if I can drive home what they mean here by the fraction of variation in Y explained by the variation in X. Well, first, let's see if we can calculate the variation in Y. And what I mean by the variation is Y and Y's, and we're going to find the variance of Y. Okay. Well, we just said that variance was the standard deviation squared. Standard deviation squared. So let us find the standard deviation in our Y. That is, what is the spread of our Y's? You can go stat, calc, one variable stats, and we want to look at our Y's, which are in list 2, second list 2. Okay. And then go calculate. Our average Y is 590. That looks reasonable. 590 appears to be pretty much in the middle. The sum of the Y's is 4,130. But this is what I want to key on. This is the population standard deviation. This is the sample standard deviation. This is the number I want. The difference between these two is the divisor. All right, but we're interested in this, the sample standard deviation. So S of our Y's, our S sub Y here, is approximately 89.81. What is this number? Well, it's the standard deviation in our Y's. It's a typical distance from the mean. Well, look at our Y's. Our mean was 590, so this is about 90. This one's very close. It's within 10. This one's like 180, 2 standard deviations away. This one's like 20, and this one's 50, and this one is 90. So you can see that this number does do as we expect it to do. This number describes a typical distance that these numbers are from it. This is my standard deviation. Okay. This is the standard deviation of my y values. Okay. All right, well, now let's look at the variance of my y's. I'm going to look at the variance of my y's because, as I stated before, it's a little better number to use mathematically. So I'm simply going to square this number. 89.81 quantity squared. That number is about 8,065.84. Okay, this is the variance of my y's. All right. You can think of this as being the variation in the y's. This is what we're seeing here. This is the variation in y. This is the total spread of my y's. This 8,065.84, and it's the unit here is in calories squared. Okay. Well, now let's look at how much variation the model explains. What am I saying by that? Let's look at this graph. All right. Here comes my best fit line. Well, my best fit line didn't hit every point. It missed the points. It missed this one by this much. It missed this one by this much. We have some unaccounted for variation. If all the points were right on the line, there would be no unaccounted for. But this residual amount is the unaccounted for portion of the model. I want to look at its variance. So what I want to do is store my residuals in list 3. So I'm going to go second stat. There's my residuals in number 7. I'm going to go down to number 7. And I'm going to store that in list 3. Okay. Enter. Now I can go to stat, and in list 3 is going to be my residuals. The first residual was negative, and the first residual is negative, the second one's positive, the third one's positive. Let's take a look. First one's negative, it's below the line. Next one's positive, next one's positive. The residual, remember, is y minus y hat. All right. So each one of those are just these little y differences in here. Well, I want to look at that standard deviation and that variance. So now I'm going to find the standard deviation of my residuals. Okay, so back to my home screen. I want to go stat, calc, one variable stats, but now I want to do my residuals, which are in list 3. All right. Again, here you can see this average and the sum, they're both 0. This is the calculator trying its best to get to be 0. But here's what I want to key on. The standard deviation is 24.95. This is my standard deviation of my residual. Okay. Again, let's go back to the data and take a look. The mean is 0. We know that. But look at these numbers, negative 11, then 26, then 3, then 27, then 2, then 37. I'm just considering the magnitude here, 26. You can see that this number here, about 25, is a good descriptor for how far these numbers are from the mean. Now I want to square this number. I'm squaring this number that we just found. 24.95. 24.95 quantity squared. All right, that is 622.5. This is the variance of my residuals. Okay, so what's the big ideal here? Well, I'm going to look at two values. This one and this one. This number here is the total variation in y, 8,065.84. This number here is the variance of my residuals. It is the part that's unexplained by the model. It's what we're not accounting for. So if I look at the fraction this divided by this would be what is not explained by the model. So the rest of it would be what is explained. The rest would be the coefficient of determination. Let's examine that. I'm going to look at this number here, 622.5, divided by this number here, 8065.84. This is my total variation in y. This is the variation that is not explained by the model, the variation in my residuals. All right, this quotient, the previous number, divide 8065.84. That is 0.077, which is approximately 0.077. That is 7.7%. So this is the variation in y not explained . 7.7% of the variation, this variation in the residuals, is not explained by the model. So that remaining 92.3% is explained. That is r squared.